Alright guys, as you can see I'm not there today. I do apologize in advance, and believe me I would much rather be there. But anyway, I hope everyone had a nice break and hopefully everyone had a good day yesterday. We are going to move on with the material, so if you guys want to get loose leaf paper, you're more than welcome to. As always, if something's in green, it's probably important, so if you want to write it down, you can. We're going to be going over a lot of examples today, but what we're going to be doing is predicting products. What I mean by this is I'm going to give you the reactants, and you guys are actually going to come up with the products and then overall balance the chemical equation. So far what we've been doing is I've been giving you the reactants, I've been giving you the products, and then we've been balancing. So we're going to just add one more puzzle piece today. So let's review what we went over already in the past. What type of reaction are the following? Obviously his reaction, it looks kind of mad. Wait a minute, this isn't chemistry. No, not this type of reaction. Haha, laugh, laugh, chuckle, chuckle. You know you like my corny joke. But no, what type of reactions? Ones we went over last week: synthesis, decomposition, single replacement, double replacement, and lastly combustion. But I'm not going to do too much with combustion with you guys until I come back. So pretty much you only have to worry about the first four there. So let's go over some examples. The first one, this is a single replacement reaction. Why this is because we have two different things on our reactant side, one of which is a compound. We have H2SO4, which is, as you already know, sulfuric acid. We have hydrogen in there, and then we have a polyatomic of sulfate. These are two different things. From now on, what we can do is we can pretend that these polyatomics are almost like their own elements. So we have two different things bonded together there. What separates single replacement from double replacement is we have to look at that other, whatever it may be, in the reactant side. In this example, it's magnesium. If this was double replacement, that magnesium would be bonded to something else. In this example, it's not. Magnesium's alone. So for our products, what we do is we are going to switch whatever the positive charged elements are. We have hydrogen, which has a positive charge, and magnesium, which has a positive charge. And when we switch them, the magnesium is going to get bonded to the sulfate, and then we're going to have hydrogen left alone. As you can see there in the products, this is what we have, but there's one thing to look at. That hydrogen, it kind of isn't alone because we got that little 2 subscript there. Why is that 2 there? It kind of doesn't make too much sense. Well, if you remember from last chapter, have no fear of ice cold bread. Hydrogen was one of our diatomic molecules. What that means is it can never exist in nature alone. So that's why we have to put that 2 subscript there. Nevertheless, this is an example of a single replacement reaction. Second example, we have calcium and we have oxygen. Again, oxygen's a diatomic, that's why we have that O2 there. For this whole PowerPoint, guys, all of our coefficients that I have in front of our elements or compounds, I wrote them in red just to help keep you guys a little more organized. So just so you know, they'll all be in red. But anyway, we have calcium plus oxygen yields calcium oxide. This is an example of a synthesis reaction because we have two different elements. Now it doesn't matter, they could be elements or they could be polyatomics, but nevertheless we have two of them, and it's yielding or producing only one compound. Easy way to remember synthesis is you will never have a plus sign on our product side. Let me repeat that. You will never have a plus sign on our product side of a synthesis reaction. That's why it's just CaO. There's no plus sign anywhere there. So this is our synthesis reaction. We have two different things and we're combining them together or synthesizing them into one product. Next example, we have calcium nitride and aluminum oxide. This is going to be a double replacement reaction, and we really don't even have to look at the products to see this because each of our reactants has more than one element in it. We have calcium and nitrogen in the first one, and aluminum and oxygen in the second one. So what we do is we are going to pick out the elements with the positive charges. This is calcium, and this is aluminum. And what we're going to do is we're just going to switch them. So that way calcium is going to be with oxygen, and aluminum is going to be with nitrogen. That's why we get calcium oxide and aluminum nitride on the product side. So this is a double replacement. In other words, both elements are switching what other element they are with. They're switching the elements. Okay? Alright, next one, we have cesium sulfide yielding cesium plus sulfur. This is going to be an example of a decomposition reaction. Now, remember when I said synthesis, you will never have a plus sign on your product side? Exactly the opposite goes for decomposition. You will never have a plus sign on your reactant side. That's why we only have cesium sulfide, no plus sign on our reactant side. So, for decomposition reactions, think of it like biology, like last year. When we had a decomposer, an organism that decomposed things, it was breaking them down and separating them into smaller pieces. Same thing happens here. Our cesium sulfide became cesium plus sulfur. What I did for this next example is I made it kind of the same thing, but I made it a little more difficult, such that I started to put your polyatomics in there. I told you guys they can come back to haunt you if you didn't memorize them in the past. But for this one, we are also doing a decomposition, but we're throwing in those polyatomics. So we have beryllium nitrate, and that's going to decompose or go through a decomposition reaction to form beryllium and nitrate. Now, again, you want to keep those polyatomics together. You don't want to separate that nitrogen and that oxygen at all because it is a polyatomic ion. Almost think of polyatomic ions as their own elements, and you're not going to separate those. Okay? Two more examples, guys. Next one, still, I'm trying to get you familiar with using these polyatomics. We have sodium plus carbonate, and we put them together to form sodium carbonate. Now, do you see a plus sign on that product side? Good, thank you for responding. That answer is no. You all seem, quite energetic today, but nevertheless, no, there's no plus sign on that product side, so we have sodium carbonate, and that's going to be a synthesis reaction. Last example, this one's a doozy. It looks intimidating, it's not. We have ammonium sulfate, 2 polyatomics, plus calcium phosphate, with only 1 polyatomic, which would be phosphate, and that's going to yield calcium sulfate plus ammonium phosphate. This one's pretty easy, and seeing it's a double replacement reaction, we have 2 different parts to each of our reactions. Our reactants. In the first one we have ammonium and sulfate. That's the first compound of our reactants. The second one we have calcium and phosphate. Each one is its own thing, so what we're doing is we're going to switch those positive charges so that calcium is going to bond to sulfate and ammonium is going to bond to phosphate. And then lastly we balance like we've been doing, and that's pretty much it. So let's move on to the new stuff. So this is what you guys want to write down. So let's start off with number 1. You are going to first determine what type of reaction it is. So make sure, guys, if you want to write these steps down, anything in green, probably important. Type of reactions we will be doing today. It could be synthesis, it could be decomposition, it could be single replacement, or double replacement. As I already said, combustion does exist, but we're going to wait till I come back to go over those ones. Second thing, we're going to assign charges to all of your elements or polyatomics. Polyatomics, you should have all those memorized because, hey, we took a test on them, you memorized them in the past. So we'll assign our charges just like we did. I'll go through the periodic table and on the next slide and review those charges with you on how to locate them there. But if you guys remember, it's +1, +2, +3, yada, yada, yada. Third, for the third one, we're kind of going back up to the first one. We're going to follow the instructions of the type of reaction that you have. In other words, if it's a synthesis, it should be A plus B yields AB. So you shouldn't have anything being added together on the product side. You'll see that as we go through some examples. Number 4, we're going to cross the charges. We did this a few chapters ago in order to come up with a product. For example, if we have, I don't know, sodium plus oxygen, our product would be Na2O because we cross the charges, and that's how we come up with our product. We'll go through some examples though. But anyway, number 5, balance the equation. We've been doing this. I think you guys are pretty good at this now. So take a minute, copy these down, and then we'll move on. If you guys need more time, just ask your teacher to rewind the video a little bit, and you can finish copying down everything in green. But you guys should be pretty much done by now. Alright, let's move on. So this is a, oh hi, this is, yes, the periodic table. Quite lovely in its gloriness, but we're going to do the charges. So if you remember, the alkali metals have a positive 1 charge. That's hydrogen, lithium. I'm not going through all those atoms. Secondly, we have our alkaline earth metals, positive 2 charge. Skip those ugly transition metals for now. We're going to go to boron, and it's going to have a positive 3 charge. We're going to skip that calcium group because, or I'm sorry, carbon group, because they mostly participate in covalent bonds. We're going to move over to our nitrogen group, which is a negative 3 charge. Next, oxygen group, negative 2 charge. And then our halogens, which is our fluorine group, is a negative 1 charge. We're not going to really mess with the noble gases, although they do have a charge of 0, because since they do have a charge of 0, what aren't they going to do? Awesome, guys, you're so energetic today. Yes, they are not going to participate in any bonds because they are neutral. Wow, that was great, guys. Anyway, let's go over some examples. So first example, go ahead, copy down what's in green for now, and then leave some space underneath because we're going to fill up that little section there. So in our first example, we have sodium plus oxygen. Now, first thing we got to do, what type of reaction is this? We have 2 different elements with a plus sign in between them. Obviously, this is going to be a synthesis reaction. All right, that's the easy part. We kind of identified what type of reaction it is, and we know that in our product we are going to sandwich or combine those 2 elements together. So second step, we got to assign our charges. Sodium, it is in our alkali metal group, in other words the one that starts with hydrogen. That is going to be a plus 1 charge. Secondly, oxygen, kind of on the other side of the periodic table, it has a negative 2 charge. So let's do what we did in the past. We're going to take that positive 1 from sodium, and we're going to move it down to oxygen. Then after that, we're going to take that negative 2 from oxygen and move it down to sodium, giving us Na2O. Isn't that fantastic? So after that, we don't really need those arrows anymore. We really don't need those charges anymore. So let's clean this up. Let's get rid of everything we don't need. There we go. Nice and pretty. So I told you guys to leave some room underneath because we have to, guess what? Just what we've been doing in the past, balance this chemical reaction. So let's look at our reactant side first. We have sodium and we have oxygen. We have 1 sodium, we have 2 oxygens on our reactant side. On our product side, we have 2 sodiums and we have 1 oxygen. Alright, I'm just going to pick a random one. I'm going to start off with my sodium. You guys might do it differently. I might actually too, but we're just going to do it this way. So if we start off, I only have 1 sodium on my reactant side, so let's throw a 2 in front of there. This makes us have 2 sodiums. In doing that, guess what happened? Our sodiums are now balanced, but our oxygens kind of still screwed up. So Let's put a 2 over on our product side. Don't forget, I cannot stress this to you guys enough because I know some of you are still making this mistake. You got to use that distributive property. You can't just do what you want. I put a 2 there, so I'm going to change oxygen and then I'm done. No. If you put a 2 in front, it has to apply to sodium and it has to apply to oxygen. So we will have now 4 sodiums and then 2 oxygens. So now our oxygens are good, but our sodiums, oh crap, yeah, they kind of got screwed up. So let's fix that. I'm going to erase this too. Let me get my eraser out here. There we go. And then I'm going to put a 4 in front, which would now balance it out to 4 sodiums on each side and 2 oxygens on each side. All right. Look what you guys just did. We took reactants. We made our product with it. We figured out what type of reaction it is. We then balanced it. This is perfect. So let's do a few more. Let's do 3 more examples. Second one, we have hydrobromic acid. Oh, going back to naming, that's scary. But anyway, we have HBr plus Ba, barium, and we got to first determine what type of reaction this is. So if we look at our hydrobromic acid, our HBr, it is going to have 2 different elements in it. Now that tells us that we can either have a single replacement or a double replacement reaction. Let's look at our other part of our reactants. It is barium. It's not bonded to anything. It's all alone. So this is going to be a single replacement reaction because barium doesn't have anything else to it. So next thing, let's assign our charges. Hydrogen, alkali metal, it's going to be a +1. Bromine, that's in our halogen group, that's going to be a -1. And then lastly, barium, that's in our alkaline earth metals, that's going to be a +2. So what I'm going to do is I'm going to bring the ones down that we're going to switch. Obviously, we're either going to switch the positives or we're going to switch the negatives. In this example, 2 of them are positive, so let's switch our positives. That's going to bring barium over and combine it with bromine. Keep those charges there, and now let's switch them. So that 1 from bromine is going to come down to barium, and then that 2 from barium is going to come down to bromine. So we should have Ba, Br2, and there it is. I no longer need all that blue stuff, so let's get rid of that. Now, what are we left with? Look at the bottom, guys. Look at the bottom of this slide. In our reactants, we have AB plus C, and then that yields A alone plus BC. Well, we already got the BC in there, so let's put the A alone. That's going to be hydrogen. So it looks like we're done here, but we got to do one more thing. We got to make sure, hey, I got that hydrogen alone. Let me make sure it's not a diatomic. So have no fear of ice cold bread. Is hydrogen involved with the have no fear of ice cold bread? Again, have no fear of ice cold bread. Yes, the have stands for hydrogen, so we got to put that little 2 subscript there, and then we're good to go. Okay? So now we're done. We found our products out. We found that hydrobromic acid plus barium actually gives us barium bromide plus hydrogen gas. So let's get rid of all this excess stuff that we don't need anymore. Last thing we got to do, we got to balance this chemical reaction. So let's start with the reactant side. We have 1 hydrogen, 1 bromine, and 1 barium. On our product side, we have 2 hydrogens, 2 bromines, and 1 barium. So let me just start up top. The hydrogens are all screwed up, so let's throw a 2 in front of our HBr, just like that. Again, do not forget, you have to use this distributive property. If you don't, you're going to get burned. So the 2 goes to the H. Bam. Done. Don't forget, has to go to the Br2. There you go. Now, are we balanced? Oh, look at that. That was actually pretty easy. We have 2 hydrogens on each side, 2 bromines on each side, and 1 barium. All right. Here comes the next one. I'll give you guys a second to write that down. All right. Again, leave some space underneath, so you have some time, or I'm sorry, some area to balance your chemical equation later on. So let's look. We have a whole lot of polyatomics in here first off. So let's look at our reactants and see, is there 2 parts to each one, or is there 2 and 1 part to each one? Okay. So we have magnesium and we have nitrate on the first one, and then we have ammonium and phosphite on the second one. Clearly, double replacement reaction. So let's start assigning our charges. On magnesium, we have a +2 charge. On nitrate, we have a -1 charge. Ammonium, +1, and phosphite is a -3. So what we can do is we can switch our positives or switch our negatives. It doesn't really matter which one. I'm going to switch the positives, so I'm going to switch Mg out with ammonium NH4. And then we are going to, I'm just going to bring the first one down. It's going to be MgPO3. Keep those charges there. And now let's flip them. So the 2 from Mg comes down to the phosphite, the PO3. And then that -3 from phosphite comes down to Mg. And we get Mg3, PO3, parentheses 2. Alright, so I'm done with that. Let me get rid of that one. And let me bring down our other pairing. We have NH4. Don't forget, guys, the positive always goes first, negative always goes second. So we have ammonium nitrate with our +1 and -1 charges respectively. So we are going to switch them as we've been doing. We really don't have to worry about anything because they're both a 1. I do apologize, I ran out of room up top, so I'm just going to write it slightly underneath. If you guys can fit it across your page, so you can keep it in line. You don't have to kind of subscript it as I did there. Alright, last thing we got to do. That's balance. You don't have to worry about doing the individual atoms. You can actually keep your polyatomics together, which makes it nice. So on our reactant side, I have Mg, one of them. How many NO3s do I have there? Yeah, let's just keep it all together. We have 2. How about NH4s, ammoniums? I have 3. And then lastly, PO3s, I have 1 on our reactant side. Let's do the same thing for the products. I have 3 Mgs. I have 1 NO3. I have 1 ammonium, NH4. And then lastly, I have 2 phosphites. So I'm going to start off with, actually I'm going to start at the bottom for this one. It just seems like a little bit easier than dealing with those magnesium with the 1 and the 3, because those might get screwed up later on anyway. So I'm going to put a 2 in front of my NH4PO3. This is going to change my PO3 to a 2, but don't forget, use our distributive property, and it's going to change my NH4 to a 6. Okay? So now my PO3s are good, but now my ammoniums are kind of all screwed up, and it's a pretty big number, so let's go there next. I'm going to put a 6 in front of NH4NO3. That leaves me with 6 ammoniums and also 6 nitrates. So now my phosphites are good, my ammoniums are good, but now my nitrates are kind of screwed up. So next thing I'm going to do is I'm going to put a 3 in front of my MgNO3, my magnesium nitrate, and this is going to change my magnesium to 3 and my nitrate to 6. Alright? So I think we're all balanced here, everything looks good, and that's pretty much all you got to do, guys. Alright, one more, so go ahead and copy this down. Okay, so if you notice, on our reactant side, there's no plus sign. So automatically it has to be, yes, we're so energetic, decomposition. Beautiful. All right, so all we got to do, these are the easiest ones. We got to break those two things apart. We have aluminum and bromine. Now, always want to make sure, always make sure there's no diatomics in there. So don't forget, have no fear of ice cold bread. The bread, remember I changed it a little bit to make it a little more appropriate for us. So bromine, bread, we need a 2 down there. And that's pretty much all we do for that one. I think these are the easiest ones out of them all. We just have to balance this chemical equation. Start with the reactant side. We have 1 aluminum and we have 3 bromines. Move on to your product side. 1 aluminum and 2 bromines. So if you look, the bromines are really screwed up here. There's no way we can like put a 2 on our product side because that's going to make it 4 and it's going to get all screwed up. So let's aim to get the 6 bromines all together. So let's put a 3 on our product side. What that's going to do is that's going to change our product bromine to 6. And now what we can do is we could put a 2 on our reactant side, making our Al 2 and our Br 6. So everything looks pretty good, but oh crap, the aluminum's got screwed up. So throw a 2 in front of there, and that's pretty much it. Alright guys, with the remaining time, I have a little worksheet for you guys to do, just a few of these. Do your best on it. There's not many of those. And then I will for sure be back tomorrow. If you guys need to rewind the video and watch any of it, just have your teacher do it. If not, you can also just watch it on your phone if you'd rather do it that way. Either way works. Hopefully you understood everything today, and hopefully you have a good rest of the day, guys. Thanks for being good today, and I'll see you guys tomorrow.